Now I will try to run a simple experiment to provoke a constriction response of the pupil. And normally this response is going to be different for two alternating conditions. We will show either a brighter or less bright gray screen, gray square on the screen. Both of them will likely produce constriction of the pupil because of the ordinary light reflex. But one of those conditions will provoke a greater constriction, which is a more bright stimulus. I will explain the structure of the protocol, which is written in MATLAB and is using few functions of PsychToolbox. First of all, try and catch loop is used to avoid errors, avoid freezing of our paradigm in case of any errors. So if an error happens, we go right to the stop recording and close all the applications functions. Here we indicate that the iLink recording will happen. First we run few functions to initialize the screen of the PsychToolbox, and this setting allows us to overcome a precise calibration of the screen, which is not necessary for most cases. Then we calculate the coordinates of the center of the screen out of this variable, screen rect. We hide the mouse cursor. We set the parameters of the fixation dot, which will be the size of 10 pixels, 10 to 10. It will be a square, and it will be of red color. And this is the syntax of the function of PsychToolbox to create this fixation dot or a fixation square. And then we run this function, screen window flip. The window is just the name of the window we are going to use all the time during our experiment, and we call this window to flip the visual information, and the flip is doing a refreshing of the image on the screen. So the dot, the red dot, will appear at this moment, and this moment, the time of this moment, is encoded in the variable VBL, which is vertical blink. The size of the square, the color will be different for two cases. Color scheme, the first row will be the gray background plus 20. We said gray background from the very beginning. And the other one will be plus 40. So this is more bright, this is less bright. But both of them should be brighter than the background. For the condition, we use blockwise randomization, which means that we do 2 loops, and during each loop we set 5 elements of the temporary array. Let's try to see how it looks. This array will look like this: 5 times 1, 5 times 2, and it is stored in this variable. Then we do randomization of the order of the conditions 1 and 2. As you can see, each time we run this procedure, it will shuffle the conditions in a different way. And then we concatenate a variable cond with this a longer array, cond 2 times 10 or 20, with more or less uniform distribution of different conditions. We don't randomize the entire 20 sample array, so that we don't get by chance agglomerating of many conditions of one kind at the beginning, let's say, of the experiment, and many conditions of a different kind at the end of the experiment. In total, there will be 20 trials, and we also randomize inter-trial interval. The inter-trial interval will be stored in this kind of variable, and it is a random value from 0 effectively to 3, maximum 3, which will be seconds. We save conditions, and probably we will save the inter-trial intervals in the res-out structure, result in output or something like this, which will be useful to track subsequently what happened during the experiment. The initial inter-trial interval will be 6, so that at the beginning of the experiment there is enough time to stabilize the gaze and the pupil. Well, the gaze will be fixed in the center of the screen, as we indicate the coordinates of the center like this. This is the center, x and y, so the width of the screen divided by 2 and the height of the screen divided by 2. And we repeat it twice, and then we add the size. Subtract and add the size of the image. Basically, it is like the coordinates of the left upper corner of the square and the right down corner of the square. The same for the small and for the large square. This is the general logic. If we indicate EL equal to 1, then this if loop is active and there is the eye tracker data. Then we wait for a second. This is the function to wait secs, and we wait 1 second, and we start recording. So from this moment, the data of the eye tracker are stored in the file which we have created at the beginning when we calibrated the system. If you want to record another session, you create another file. This is how it will be more easy to operate the data. Now the main loop. This is the main loop with 20 repetitions. So it will loop 20 times, which corresponds to our 20 trials. For the baseline, so for the baseline, we show the fixation rectangle, fixation dot, which will be a red dot in the center of the screen. And in order to show it, we refresh the screen. And we refresh it at the time point. This is the variable which tells us in terms of the MATLAB clock when to do this refreshment. And it is VBL plus intertrial interval, the current element of the intertrial interval, which corresponds to the number of the loop. And the previous VBL is measured here after the first flip. So since it is 6 seconds, it waits 6 seconds after this moment and makes the first refreshment. Afterwards, there will be stimulus onset, preparation. So the stimulus rectangle of the color corresponding to the condition. Let me show what is the logic here. So if we run this portion of code, we will see the matrix 2 by 3. So the first row is for the color of the first condition, and the second row is the color for the second condition, which will be the brightest one. So if we type something like this, color stim 1 and colon, it will give us 3 values of RGB for the first condition, and it will be second. It will be 3 values for the color of the other condition. And since there are always different values of the variable cont, the first one is 1, the second is 2, the third is 2, so on. In a random order, it will present either condition 1 or condition 2 of different colors, but of the same size, since the rec_stim parameter, which is the dimension parameter, is always the same. So first goes the stimulus, then goes the fixation point. Therefore, it will be at the top of the stimulus. And finally, there will be a flip after 3 seconds of baseline. In addition to the intertrial interval, the baseline will last as long as 3 seconds. This VBL plus 3 seconds will be stimulus onset. And at this point, if we select to record the iLink data, we send a message to iLink that we start stimulation. And for having more information about the time course of our paradigm, we record the VBL of this event. So when exactly, from the point of view of the display computer, happens this onset. And the stimulus offset, we do exactly the same as for the onset, but without the stimulus. So this element is absent here. But the fixation point is there. It should always stay on the screen, in the center of the screen. And we give the duration of the stimulus of 1 second, which will be more than enough to provoke a constriction of the pupil. And the VBL from here will be also stored in result, but for the offset, for the current trial. At this moment, as soon as we flip the screen, we send another message to the iLink, which is called stop stim. Start stim, stop stim. Later, we will be able to decode the precise temporal location of the start and the stop. And hopefully it will be exactly 1 second, but most likely not. There will be some error, but we don't care about it for the moment. What we care about is that when all the 20 trials are over, we give another 6 seconds to stabilize the post-stimulation time series. We wait another second and we stop the iLink. Stop recording and shut down the system. And afterwards, we measure the clock, the current time, and we use this information to call our results file, where we store result in MATLAB. It will contain all the information about the order of the conditions and the temporal structure, what is measured by MATLAB. And then we close all the windows of PsychToolbox. That's it. It's a pretty short script of about 100 of lines. So let's check again if everything is fine with the calibration and run our experimental task. We show window of pop-up calibration. This is the file name where all the data will be stored. We run camera setup. Press enter in order to check. You see, I somewhat shifted from the center. Well, everything looks okay. Let's redo the calibration and the validation. Yep, validation. Looks okay. And at this moment, we can try to run the paradigm, and let's hope that it will run well. As soon as the eye tracking data start being recorded, there will be a change in the host computer, which will be recorded by the other video. So the fixation dot is there, and we see the white, the gray screen, the square. Another one. Not so intensive. More intense. I try to blink as little as possible, but I will intentionally destroy one of the trials with many blinks. This one. Blinks are very bad for the eye tracking or pupillometry. It's better to avoid them or to minimize them. But they happen unintentionally from time to time. And this is what we are going to try to resolve at the stage of the artifact detection during the data analysis. The task is not going to be very long. And the signal must be pretty powerful, despite the fact that I was distracted during the procedure. So the data is recorded, and now we can close the file. The chart sphere is finished, and if we go to the documents, we will find this folder, and this folder contains the file with today's date, with the extension of EDF. This is a useful file, and we copy all the folder to the folder where the res_out file, the MATLAB data file, is stored. So let's call it 2020 09 29 1. VB. Subject is myself. We store here the data from the eye tracker, and we put the data from the MATLAB PsychToolbox paradigm, and we also copy the PsychToolbox script, the MATLAB PsychToolbox script, so that we remember how did we run all this experiment. And then we can work on the data analysis.